Hey everyone, hey Twinnies, welcome back. So I'm assuming that you've done this question yourself and you're just here for the quick answer solution. So determine the refractive index of class to correct one significant figures. Well, they're giving you the formula and they're giving you the values and they just want you to punch it into your calculator. So what you'll get from here is 1.35 minus 0.2 divided by 1.35 minus 0.59, and that should come out to about 1.51315. But they want to the correct number of significant figures. And if you look here, 0.20, you may think that this is 3, but you'd be wrong. This is 2, because there's 1 here, 1 here. This does not count. This does not count. This counts, this counts. This counts, this counts, this counts. So this is actually 3. And when we quote significant figures, we quote it to the smallest value. How can you kind of figure this out? Well, the easiest way for me to do it is that you just think about what would this look like if I quoted it in significant figures terms. So for this case, it would look like 2.0 times 10 to the minus 1, 5.9 times 10 to the minus 1. That's 2 values. The other 0 doesn't matter. In this case, if you were to quote it, you'd quote 1.35 times 10 to the minus 0, because there's nothing. But you see, there's 3 values. So this 0 counts because it's stating that 0. Like, this is a 0 instead of a 1. And then this 0 doesn't count. So, how many values do they want? Well, they don't want these ones. And they don't even want this one. So it's just 1.5. And that'll get you the first mark. If you put any more than values than that, you don't get the marks, because that means you don't understand significant figures. Next, calculate the uncertainty in A1. Now this one's a little bit more tricky, but it is very much doable because you just use the basic rules of uncertainty calculations. So to make this a bit easier, I'm going to assume that x1 minus x3 minus x1 is equal to A, and x3 minus x2 is equal to B. And then, so essentially what we have is the refractive index is equal to A on B. And that means the uncertainty in N is equal to uncertainty on A plus the uncertainty of B on B. And that means we can just multiply this out by N. So we get here that. And how can we find delta A? Well, that's simply delta A, because it's x3 minus x1 is equal to delta x3 plus delta x1. So we just add them. And what are they? Well, this one's 0.02, and they're all 0.02, so they're actually all the same. So that's just equal to 0.04. And delta A, since these are kind of the same, is also equal to delta B. We also need to find A, which is equal to 1.35 minus 0.2. This one's equal to 1.35 minus 0.59. This is equal to 1.15, yes. And this one's equal to a calculator, hello. Don't do the math if you have a calculator. That's the biggest tip. 0.76. And then now we have all the numbers, and we know N from our previous equation is this. So this just becomes a matter of, after we figure this out, we can just punch stuff into the calculator. So, our delta N is equal to delta A on A, that's 0.404, on A, which was 1.15, plus delta B, 0.04, on 0.76, multiplied by 1.5, and that comes up to about, let's just check, 0.04. I'm just checking on my calculator. You should do the same. Unless you've already done this, because you're a genius. times 1.5, and that comes out to about 0.1311. Oh no! Okay, another significant figures test. Right. So let's look here. 0.21 is 0.02. This is the uncertainty, and that is only one decimal place, because if you were to write in significant figures term, you would write 2 times 10 to the minus 2. You wouldn't write 2.0 because there's no O there. They didn't say that. So they want it to one significant figure, and that means in terms of rounding, we just get rid of all those, and then the uncertainty is 0.01. 0.1, and that gets you the 3 marks. After the experiment, the student finds that the traveling microscope is badly adjusted so that the measurement of each position is too large by 0.05. Oh no. Okay, so in this case, what's happening is kind of like this, in that all of the values have been shifted up a bit because of the measurement. And what we call this a systematic error. And how do you know it's systematic? Because there's something wrong with the system, damn it. Systematic. The issue is that this is different from, now remember that there are only 2 types of errors. There's random errors and there's systematic errors. Random errors are things like, can be improved by repeating experiments. So if you measure the temperature of a room and you measure it again and again, there's going to be a random error with different there's going to be some sort of random error, because every time you measure it, it's going to be different every time. And that can be improved by repeating the experiment over and over again. But then there's the type of errors which happen when there's something wrong with the measurement. For example, if you have a ruler, right? Oh, terrible ruler. But stick with it. And then you start, instead of measuring you have like a lollipop. You have like a lollipop that you want to measure. And you measure it, and you measure your lollipop, instead of measuring from here, which is the 0 point, right? You measure from the top. So that means your value for the lollipop is there. So it's actually, but then in reality it's not there. It's actually, you actually have to measure at the 0 point. So you measure the lollipop shorter than it actually was. And then you do a bunch of measures with other lollipops, and it comes out, and the same thing happens, in which they're all just a bit too short. That means there is something wrong with your system, and it is a systematic error that is causing your problem. So that's how you know that. And you know that because each position is too large by 0.05. Now I want you to outline the effect of the error B1 will have on the calculated value of the refractive index. Now in this case, the refractive index is acting somewhat like the gradient here. In that even though there's something very wrong with this and that everything is shifted up, the gradient is still the same. This is what happens with the error calculated of the glass. So what's happened is that all of these values are too large by 0.05. So x3 becomes x3 plus 0.05 minus x1. This also is plus by 0.05. And that's all over x3 plus 0.05 minus x2 plus 0.05. And if you take this out, what you find is that you can take that out, and you find that it just cancels itself away, because the denominator and the numerator remain unchanged. And then you just come back to the normal refractive index. So, Actually, so what happens is that there's no effect. As the numerator and denominator remain unchanged. And that'll get you 2 marks for each point. Then it says, after correcting the adjustment of the traveling microscope, the student repeats the experiment using a glass block 10 times thicker than the original microscope. Explain change, if any, due to the calculated result of the refractive index and its uncertainty. From this I can tell, okay, so you get a point for this and a point for this. Now, the first one honestly just takes some logic to answer. No weird physicsy equations. Just use your common sense. So, you have a block like this versus a block like this. And it's asking you, how does the refractive index change? Now, in other cases, what do you know about the refractive index? When does it change? It doesn't change if you increase the size of the block. It only changes if you increase the type of material. So, like, if you increase this, if you have this block, and you put on top of that block, the refractive index doesn't change because it's still the same block. So actually, the refractive index, again, does not change. Because refractive index only changes when you change the type of material. Secondly, now it also asks us to look at the uncertainty. Now, if we look here, right? What does x3 minus x1 correspond to? x3 minus x1 is essentially the width of this block. x3 minus x2 is essentially the width here, right? x3 minus x1, you get it? And so, if we make this really, really thick, that means that x3 and x1 are going to increase. And x3 and x2 are going to increase. And how does that affect the uncertainty? Well, remember x3 minus x1 is equal to A and x3 minus x2 is equal to B, right? So what's going to happen here is that you're going to look back at your uncertainty equation and you're going to realize that, hey, this is going to increase whilst this stays the same. And this is also going to increase. These are going to go up and up. And what's going to happen is that's going to make your uncertainty much more smaller because you're dividing by a much larger number. So the key here is to twig that the key here is to twig that uncertainty but absolute will be smaller. You might want to say here that numerator and denominator both 10 times larger. Because that's what's happening here, right? Because what's happening here is that these are all being multiplied by 10. So it's actually 10 times that and 10 times that. And what happens is those two cancel out and you just get left back with the same thing. So yeah, that's that question done. And I hope you got all the marks, and just keep studying and keep practicing, and yeah, watch these videos and you'll eventually improve.